Hello, my name is Jingyi Zhang and I'm from University College London. Today I will be presenting our paper on single actor controlling multiple avatars for social virtual realities. Let's start with the motivation. Social virtual realities has gained popularity in various fields, including entertainment like VR shows and theaters, professional training for educators and healthcare professionals, and psychological research. A key element of social virtual reality is facilitating social interactions between users and multiple virtual humans. Despite advances in crowd generation and AI agents, existing technology still struggles to create virtual humans that respond naturally in open-ended scenarios where users have full freedom in interactions. While technology advances may eventually enable the creation of realistic virtual humans capable of natural interactions in VR, human intervention remains essential for directing the narrative, enhancing the credibility of the experience, and managing unforeseen situations. In such cases, rather than adding new virtual humans to a scene, it can be more practical for an actor to take control of a virtual human already present in the environment. Therefore, we build a system based on our previous work that enables a single actor to control and embody multiple virtual humans. Similar to the original, virtual humans are animated with pre-recorded motions during non-interactive phases, and the actor takes over control when interaction is needed. The upgraded system supports full-body avatar with 6-point tracking and features a simplified takeover procedure. Additionally, we introduced a voice modulator that adapts the actor's voice to match the unique voices of different virtual humans. On the left is what the user sees. They can view the multiple virtual humans in the scene moving naturally. On the right is what the actor sees. When interacting with the user, the actor takes control of a selected virtual human, following the role and script for the character. When not interacting, the actor observes the scene and prepares for the user's next interaction with any of the virtual humans. Now, how does the system work? The actor decides which virtual human to control and selects that virtual human through the map panel attached to their left hand. Once selected, the actor's view turns black as the system simultaneously teleports the actor to the virtual human's location. During this process, the system adjusts the voice modulator's settings, raises or lowers the camera position to match the virtual human's eyes level, and changes the actor's avatar. At the same time, the system searches within a 100-frame window to find the posture in the recorded animation that best matches the actor's current posture. If the search result is frame X, then from the user's perspective, the virtual human continues to play the recorded animation until frame X. Then a blending animation smoothly interpolates the virtual human from recorded motion to the actor's current posture. Once the blend animation is complete, the actor's view turns to normal, and the actor is ready to interact with the user. We conducted a user study to explore participants' reaction to multiple virtual humans being controlled by a single actor during interactions, and to assess whether this method enhances co-presence. We compared our approach with the Wizard of Oz setup, which simulates character control methods by triggering responses based on user input, similar to how it is done in modern game development. We created a virtual museum with 5 unique virtual humans. Participants took on the role of an intern on their first day of working. A supervisor explained their task, which was to collect feedback from the visitor and report it to the colleague. We designed 5 virtual humans with distinct roles and response styles: a supervisor, 3 visitors, and a colleague. The measure included a questionnaire followed by an interview. There's 40 participants in total. Our hypotheses were the number of human-controlled virtual humans perceived by the participants in seed takeover will be greater than seed recorded. The number of humans perceived interacting with the participants in seed takeover will be higher than in seed recorded. Co-presence perceived by the participants in seed takeover will be higher than in seed recorded. Okay, the result. The quantitative results from the questionnaires are shown in the bar charts. The number of human-controlled virtual humans reported in seed takeover with a mean of 3.2 was higher than in seed recorded with a mean of 2.3. Participants perceived interacting with more humans in seed takeover with a mean of 2.65 compared to seed recorded with a mean of 1.8. Co-presence scores for seed takeover were higher than for seed recorded, so all of our hypotheses were accepted. Participants discussed why they perceive some virtual humans as human-controlled. They've mentioned initiating interactions. They expected virtual humans to look at them when approached. Some sensed an active range, while others felt virtual humans should respond only after being spoken to. Quick response speed suggested human control, but delay were sometimes seen as network lag. Participants expected relevant and detailed answers. Repetitive or overly fluent responses seemed scripted. More interactivity and natural body language made virtual humans feel more human. In contrast, stiff movements were seen as robotic. Facing direction and human-like audio added to this impression. Motion realism, such as reluctance or seriousness, made virtual humans appear more human-controlled. Participants identified several factors that helped them determine if virtual humans were controlled by the same person. Voice, tone, and accent were crucial. Some participants noticed similar sounds between two visitors, while others found them distinctly different. Even when tone and accent sounded similar, distinct voices of genders lead them to perceive separate humans. Attitude also played a role. Participants noted different communication styles, such as positive or neutral, influencing their perception of separate controllers. 6 participants made assumptions based on the feasibility of the technology. They suspected one person could control all the interactions, especially since the virtual humans didn't interact with each other. We invited 4 participants with performance experience to provide feedback on our system. This partly addresses a limitation of the main study, where the actor was the experimenter with substantial prior knowledge of the system's operation. This test demonstrates that little training is required for novice actors to portray and switch control between multiple virtual humans, thereby evaluating the feasibility of the system. For future work, we aim to address 4 limitations of our system. First, the blending animation is currently linear and depends on the distance between poses. We plan to explore generative models for smooth transitions. Second, the non-interactive animations are relatively simple. Motion generation techniques could enhance behaviors during these phases. Third, choosing which virtual human to control can be challenging. We are considering the use of a director or AI assistant to help actors decide the next steps. Additionally, content summarizes and AI-generated replies could ease the transition for the actor. Finally, the system has potential to handle densely populated environments. We aim to explore multi-actor control for crowded scenes and plan to integrate hand tracking and facial recognition for more realistic movement and behaviors.